Hello viewers, in the previous episode we have discussed about the detailed properties of the p block elements. In continuation, today we shall be talking about the major applications of halogens, then the basic properties of halogens, interhalogens, classification of interhalogen and its structure, properties of interhalogen and the polyhalide, their structure and properties. Fluorine is a pale green gas. It is highly toxic in nature and can cause severe burns on contact. Hydrofluoric acid was used for etching glass. Etching glass means creating art on the surface of glass. Oil industry used it as catalyst to increase the octane rating in gasoline. The fluorine is also used in Teflon. Teflon is also used as the lubricant in the underwater machinery like marine machineries. This Teflon provides a non-stick surface for frying pans and other cooking related products. Teflon is used as solid lubricant also. This is used in World War II. The bombs dropped on Japan in 1945 produced by diffusion of the compound uranium hexafluoride UF6, which consists of molecule containing one uranium atom and 6 fluorine anions. This is the way how the etching of the glass is done. It is the non-stick cookware which has been prepared by using Teflon. It is the structure of the Teflon. This Teflon is being used as the gasket, the Teflon tape. So, these are certain applications of fluorine. The chlorine gas is also poisonous, highly irritating to the mucous membrane of the nose, mouth and lung. The concentration of chlorine used against troops on both sides in World War I was much higher. The chlorine is used as to disinfect drinking water and swimming pools. Sodium hypochlorite is used in bleach. The hydrochloric acid is used as acid in industry and laboratory. Chlorine is used in many polymer, pharmaceuticals and to sterilize hospital machinery and limit the infection growth in hospital. This is the setup for the treatment of water for the disinfection. It is the chlorine solution tank which has been attached with the tank of water. This is the supply of the water, and after that the chlorinated water can be collected through the outlet. This is the reaction of chlorine with water which is forming the hypochlorous acid. This hypochlorous acid is converted into the nascent oxygen, and this nascent oxygen is going to kill the germs. So, this is the three-way action of the bleaching powder. If you go, firstly it is bleaching powder forming the chlorine, and then chlorine forming hypochlorous acid, nascent oxygen, and that is the way how the purification of water is taking place. In agriculture, chlorine is used in pesticide. Chlorine is used in chlorofluorocarbon, which have been used in refrigerants such as Freon and propellant for aerosol sprays. Bromine, which is originated with the Greek word stink, meaning to stink, is a foul smelling liquid. Its vapors are highly irritating to the eyes and throat. It is used in dyes, flame retardant, gasoline production, production of photographic film. This fluorine is also used in drugs treating pneumonia and Alzheimer disease. It is used in pesticide methyl bromide. This is the tetrabromobisphenol A, TBBPA, which is a flame retardant, and such type of materials can be prepared which is a flame proof rotary switch of this type. Iodine is an important element for the proper functioning of thyroid gland of the body present in thyroxine. It is also used as an antiseptic. The solutions are used to clean open wounds likely contain iodine. Silver iodide is used in photographic development. The last element in this 17th group is astatine. The 211 astatine, the radioisotope, has been used in study of cancer tested by applying in mice. The halogen lamp is used for automobile headlight, spotlight, under cabinet lighting and floodlights. It is the presentation for the goiter. This is the status of the normal thyroid gland, and this thyroid gland, it is getting increased in the volume of the glands, this representation, and this is the state of the throat in such type of deficiency. It is all appearing due to the lack of the dietary iodine, which is going to cause such type of swelling of the throat. It can be treated with the potassium iodide solution or Lysol's iodine. This is the halogen lamp, which is having wide applicability. The halogen lamp is a type of incandescent lamp. The halogen gas, iodine or bromine, combines with tungsten atoms as they evaporate and redeposit them on the filament. Thus, the filament longs last. So, the durability of the filament is getting increased and it produces more light and heat per unit energy. Quartz halogen, quartz iodine, iodine cycle increases the effective luminous efficacy. Now, come to the topic basic properties of the halogen. The elements typically becomes more basic or metallic on moving down in a group. Hence, in group 14, 15 and 16, the heavier members like tin, lead, bismuth and polonium are metallic in nature. The metallic properties decrease on moving across a period. Thus, trend of metallic properties is less obvious in group 17 of halogens. The increasing stability of positive ions indicates an increasing tendency to basic or the metallic character. It must be noted that iodine is not a metal, yet we have discussed. The fluorine is most electronegative element. It has no tendency to form positive ions. Hence, fluorine has no basic properties. Iodine dissolves in oleum. Oleum is nothing but it is fuming sulfuric acid and other strongly oxidizing solvents, which forms bright blue solution, and this solution is paramagnetic, and these solutions contains I2 plus cation and not in the form of iodine cation I plus. The bromine also dissolves in oleum and forms dibromium cation and is bright red colored and paramagnetic. So, if you compare here for the fluorine, this iodine is having the bright blue solution and this bromine is forming the bright red colored solution. Both of them are paramagnetic, and this cation of the chlorine has been observed spectroscopically in the discharge tubes. Several crystalline compounds containing I2 plus or Br2 plus have been prepared. This is the way how this positive species of iodine I2 plus has been prepared. This I2 plus, and it is for the Br2 plus with the antimony pentafluoride. It is antimony trifluoride is going to react with iodine. The bond length in bromine cation is 2.15 and 2.27 angstrom is there found in pure bromine molecule. Thus, bond in cationic bromine is shorter and is stronger than that in the neutral molecule of the bromine. It is for the cation it is 2.15, which is relatively short than that in the neutral molecule. So, it is obvious that electron must be removed from an anti-bonding molecular orbital ABMO. This anti-bonding molecular orbital is having higher energy compared to that of the bonding molecular orbital. Similarly, bond in I2 plus, the cation of iodine is stronger than iodine molecule. Many other compounds containing trichlorine positive ion, tribromine positive ion and triiodine and pentaiodine positive ions have also been prepared. And this is the presentation of the various reactions involved, how the tri-positive chlorine, trichlorine with positive charge, tribromine with the positive charge and triiodine with positive charge, pentaiodine with positive charge has been prepared. The structure of compounds containing cationic halogen ions like tribromine cation and triiodine cation have been determined by X-ray analysis and Raman spectra. These ions are always bent in contrast to triiodide ion, the I3 minus, which is linear in nature. In molten state, both iodine chloride and iodine bromide conduct electricity. Electrolysis of the iodine chloride liberates iodine and chlorine at both electrodes. It suggests ionization as this iodine chloride is going to get dissociated I2Cl and ICl2. The molten iodine cyanide also behaves as iodine chloride. This is the way how it is getting dissociated. Iodine chloride behaves as electrophilic iodinating agent. It converts acetanilide to 4-iodoacetanilide. When a solution of iodine in an inert solvent is passed through a cation exchange resin, some iodine is retained by the resin indicating the presence of iodine plus. This iodine is getting treated with the resin, and this is the way how iodine is getting retained by the resin. The positive ion retained may be eluted with potassium iodide to find out amount of iodine cation, or it may be allowed to react with certain other reagents. This iodine cation is been released or eluted with potassium iodide. Here this iodine cation is being eluted with anhydrous sulfuric acid, and also it can be done by the alcoholic nitric acid like this. Iodine cation reacts with hydroxide ion in aqueous solution like this. Due to this, iodine cation will only exist in water if it is stabilized by coordination to some other molecule. A large number of compounds are known which contain iodine cation stabilized in a complex ion. Many pyridine complexes are known, such as iodine pyridine complex with nitrate, iodine pyridine complex with chlorate, acetate and benzoate like this. The molten iodine trichloride has a high conductivity and liberates iodine and chlorine on both electrodes on electrolysis of iodine trichloride. This iodine trichloride undergoes the ionization like this. Treating iodine with fuming nitric acid and acetic anhydride gives the ionic compound like this, iodine triacetate. When a saturated solution of this iodine triacetate in a acetic anhydride is electrolyzed using silver electrode, then on cathode 1 equivalent of silver iodide is formed for every 3 farads of electricity passed. This is the way how the ionization gives the tri-positive iodine. There is no structural evidence for presence of tri-positive iodine. Other ionic compounds like iodine phosphate IPO4 and iodine fluosulfonate may also contain tri-positive iodine. Next is the interhalogen compound. The molecules of interhalogen compound is formed by union of two different halogens only. The halogens react together to form interhalogen having the general formula XYN, where N is 1, 3, 5 or 7 and X is the less electronegative of the two halogens, means out of X and Y, X is less electronegative. There are never more than two different halogens in a molecule. The less electronegative element is placed onto the left in the formula and naming is done straightforward in the sequence. It is the classification of the interhalogens. These molecules of interhalogen has been classified as AX type as chlorine fluoride, bromine fluoride, bromine chloride, iodine chloride, iodine bromide. It is AX3 type chlorine trifluoride, bromine trifluoride, iodine trichloride, and AX5 type chlorine pentafluoride, bromine pentafluoride and iodine pentafluoride. And it is the AX7 type of interhalogen, the iodine heptafluoride. The interhalogen compounds of type AX and AX3, these two compounds are found between the halogen having very low electronegativity difference, particularly between the chlorine and fluorine like that. And it is again the examples of these interhalogen compounds of fluorine, chlorine and bromine, and it is having these compounds with chlorine, bromine and iodine formed, and these rest part is not having a formation of any such type of interhalogen compounds, means the compound of fluorine with bromine, iodine and astatine or chlorine with bromine, iodine and astatine has not been seen. Similarly, bromine do not form the interhalogen with iodine and astatine. This iodine and astatine is having very less possibility of formation of interhalogen. Let us see the structure of the interhalogen. The structure of interhalogen follows the valence shell electron pair repulsion theory. The VSEPR theory states the maximum repulsion is existing between the lone pair of electrons and minimum between the bond pair of electrons. For AX3 type of interhalogen molecule, it is having T-shaped structure with two lone pairs on equatorial position of a trigonal bipyramid. The AX5 type of interhalogen has a square pyramid structure with unpaired electrons in axial position of an octahedral. For AX7 type of interhalogen, it is having pentagonal bipyramidal geometry. This is the geometrical presentation of the bromine trifluoride having the T-shaped structure. This is the bromine trifluoride structure. It is a square pyramid structure of IF5 AX5 type. This is iodine pentafluoride. It is pentagonal bipyramid structure of iodine heptafluoride IF7. It is pentagonal bipyramidal. These 5 fluorines are in one plane and these 2 fluorines are above and below the plane of this pentagon. The properties of AX type diatomic interhalogen. Their physical properties lies between parent halogen. Chlorine monofluoride, the lightest interhalogen, is a colorless gas with a boiling point minus 100 degree centigrade. Bromine monofluoride has not been obtained in pure state yet. Similarly, iodine monofluoride is unstable in nature. Bromine monochloride is an unstable red brown gas with a boiling point 5 degree centigrade. Iodine monochloride consists of red transparent crystals which melt at 27.2 degree centigrade. Iodine monobromide, it melts at 42 degree centigrade and boils at 116 degree centigrade to form a partially dissociated vapor. Chlorine trifluoride is a colorless gas. It is AX3 type of interhalogen, the tetraatomic, which condenses to a green liquid and freezes to a white solid. This chlorine trifluoride reacts explosively and it is used in uranium hexafluoride bomb, what I have discussed used at the time of First and Second World War. The bromine trifluoride is a yellow green liquid which conducts electricity. It reacts with many metals and metal oxide. This bromine trifluoride is used as fluorinating agent. It is the tetraatomic interhalogen iodine trifluoride is a yellow solid which decomposes above minus 28 degree centigrade and not much is known since it is unstable species. Iodine trichloride forms lemon yellow color crystal which can melt to brown liquid. It reacts with many metal chlorides to form tetrachloroiodide and hydrolyzes in water. Next is hexa-atomic interhalogens, the chlorine pentafluoride. It is a colorless gas. This chlorine pentafluoride reacts violently with water and most metals and non-metals. Bromine pentafluoride is a colorless fuming liquid. It is physically stable but reacts violently with water and most metals and non-metals, same as chlorine pentafluoride. Iodine pentafluoride is colorless liquid again and it is highly reactive even slowly with glass also. It reacts with elements, oxides and carbon halides. All interhalogens are volatile at room temperature. These are all the general properties shown by the interhalogen. These interhalogens are polar in nature due to difference in their electronegativity value. Generally, these are covalent liquids or gases due to a small electronegativity difference among them, the constituent atoms of halogen. Some compounds partially ionize in solution. The interhalogen compounds are more reactive than normal halogen except fluorine. The interhalogens are all prone to hydrolysis and get ionized. The interhalogens form halide and oxyhalide ions when exposed to water. With bromine pentafluoride, this reaction can be explosive. The interhalogens are mostly halogen fluorides and all but 3, the iodine monobromide, the astatine bromide and astatine iodide of the remainder are halogen chloride. The oxidizing power of an interhalogen increases with the number of halogens attached to the central atom of the interhalogen as well as with the decreasing size of the central atom of the compound. All interhalogens are diamagnetic in nature. Greater the difference between electronegativity of two halogens in an interhalogen, the higher will be the boiling point of the interhalogen. Means this boiling point is related to the electronegativity with increase in the difference of electronegativity between the two halogen, the boiling point is supposed to get increased. Most of interhalogens composed of lighter halogens are fairly colorless, but the interhalogens containing heavier halogens are deeper in color due to their higher molecular weight. The interhalogen compounds of type AX5 and AX7 are formed by larger atoms having low electronegativity with the smaller atoms having high electronegativity, means a combination of low and high electronegativity is going to form AX5 and AX7 by the larger atoms with low electronegativity and smaller atoms with high electronegativity. It is because it is possible to fit the greater number of smaller atom around a larger one. For example, bromine pentafluoride, iodine heptafluoride. The bonds are essentially covalent because of a small electronegative difference, and the melting and boiling point increases with increase in electronegativity difference. The chlorine trifluoride is the most reactive of the XY3 type of interhalogens. Iodine trichloride is least reactive in the group. Bromine trifluoride has the highest thermal stability of the interhalogens with 4 atoms, and iodine trichloride has the lowest value. The chlorine trifluoride has a boiling point of -12 degrees centigrade. The bromine trifluoride of the same group has a boiling point 127 degrees centigrade and is a liquid at room temperature. However, iodine trichloride ICl3 melts at 101 degrees centigrade. The next topic is polyhalides. Polyhalide is a halide containing more than one halogen atom in a molecule. The halogens or interhalogens react with halide ions to form polyhalide ion. The solubility of iodine and formation of triiodide is a better example to understand the polyhalides. Iodine is only slightly soluble in water, and this solubility is 0.34 grams per liter. Its solubility increases in presence of a small amount of iodide ions. Suppose you have taken the potassium iodide solution, then the solubility is getting increased, and it has been explained as appearing due to the formation of polyhalide ion, particularly triiodide ion. It is quite stable in ionic crystal and also in aqueous solution. So, this is the way how the triiodide ion has been formed in a solution of potassium iodide. The structure of the polyhalide. Polyhalides always have the heaviest and least electronegative halogen as central atom, making the ion asymmetric in some cases. Structure of most heteropolyhalogen ions and lower isopolyhalogen ions follows valence shell electron pair repulsion theory. However, there are some exceptional cases also. For example, when central atom is heavy and contains 7 lone pair such as bromine hexafluoride anion and iodine hexafluoride, they have a regular octahedral arrangement of fluoride ligand instead of the expected distorted one due to the presence of stereochemically inert lone pair. The polyiodide ions have much more complicated structures like trichloride ion, tribromide ion, iodine dichloride ion, iodine dibromide ion, including triiodide ion. In these ions, one of the halogen atoms or halogen atom larger in size undergoes sp3d hybridization, giving a linear shape, and this linear shape is associated with 3 lone pair of electrons at the equatorial position. Trichloro positive ion, tribromo positive ion, triiodo positive ion and iodine trichloride positive ion. Here the central atom is sp3 hybridized, giving a bent shape with 2 lone pair of electrons on the central atom. The polyiodide ions have much more complicated structure. These ions having the central atom involving sp3d2 hybridization, giving a square planar shape with 2 lone pairs of electrons on the axial position, means above and below the plane. These polyhalide ions having the central atom involved in sp3 hybridization, giving a distorted tetrahedral structure with 1 lone pair of electron on the equatorial position. I7 minus and IFC minus such type of polyiodide ions Here the central iodine atom undergoes sp3d3 hybridization, giving a distorted octahedral structure with lone pair of electron. This I7 plus polyhalide ion, the central iodine atom involves sp3d hybridization, giving an octahedral geometry. The polyhalide ions have much more complicated structure. Fluorine, due to its highest electronegativity and having only -1 oxidation state, does not form the polyhalide ions where it acts as a central atom. Let us see some of the major properties of polyhalides. All the polyhalides are colored compounds. The depth of color increases with increase in atomic number of halogen atom present, means larger the atomic number of halogen, deeper will be the color. Thus, bromoiodides are red and chlorobromides are yellow in color. Polyhalides are usually soluble in water, from which they can be crystallized. Some of them gets dissolved in water to free halogen and halide ion. This is the dissociation of triiodide to dissociate into iodine and iodide ion. The stability of metal trihalide proceeds in order as this from iodine to chlorine. Some of the polyhalide ions form complexes with organic donor molecule like this. When solid polyhalides are heated, they dissociate more or less readily. The ease of dissociation of a given polyhalide decreases with increase of size of cation and with which the polyhalide ion is associated. On thermal dissociation, the polyhalide gives metal monohalide and halogen or interhalogen molecule like this. This is the cesium triiodide, which is getting dissociated on thermal dissociation as cesium iodide and the iodine molecule, and here it is going to produce a molecule of interhalogen iodine chloride along with this halide. Let us see that we have discussed the major applications of halogens, and in the previous episode we have discussed the properties of the halogen. Further, the basic properties of the halogens were discussed in details. The interhalogens compounds constructed within the two halogens, their classification and structure of the interhalogens were discussed in detail. The structure based properties of diatomic, the AX type, tetraatomic AX3 type and hexaatomic interhalogens were also been discussed. The general properties of interhalogens were presented. The polyhalides and their structures were discussed along with their general properties in detail. Thank you.